All right. Close on. Rachel.
Before we start, for AFCE, we have an event tomorrow.
Sure. Sure.
So for AFCE tomorrow, there's an event at 11 at the ERC, which is just off Second. And Jared, a master student, will be testing his his bank loan testing. It's at 11 a.m. if anybody wants to come.
Okay, did those online hear that? Okay, wonderful. All right, yeah, it's a pretty impressive physical model of, I think, half scale ITD bridge. So if you're interested in that sort of thing, it would be a great opportunity to see testing in Norris. All right. Any other questions before we get going? No questions? Okay, I do want to point out one thing here. In doing the homework that's due tomorrow at noon, sorry about that. I haven't turned on the, let me share my screen here. Okay. All right, there we go. So in doing the homework, you're working with minor losses. And this kind of will give you an idea of the range of minor losses, if you will, or how two different people come up with two different answers. The first problem, there's elbows that are associated with it. And if you come in here and say, oh, 90-degree elbow, it's going to be 0.021 to 0.03 for each elbow. But you'll also note that the problem statement said that it was threaded minor loss, or it was a threaded elbow. Now, why would a threaded elbow be different than a regular elbow? Okay, yeah, we got threads in there, right? And we don't run the pipe necessarily all the way to the end of the threads. We just take it in there until it's a tight fit. So those extra threads as the flow goes across could be additional. So if you come over here, threaded pipe fittings, you'll see that a 90-degree elbow is 0.9. Okay. Now you could also come up here and say a smooth bend, but you need the radius and the diameter for that. So for this particular problem, probably the best option, because it is noted that it's a threaded elbow, is that you would use this 0.9, that K value right there. Okay. The other thing I wanted to point out, and I kind of alluded to this when I posted the homework, is that when you have a tank, or when you have a pipe going into a tank, let's do it like this. If I call this 0.2, and we say that is versus, okay, the pipe that comes out like this, and it's a free discharge, and we call this 0.2. Okay, what is the difference there? And this kind of fits in with what we're going to talk about today. What is the difference between these two? When I write the energy equation, so if I was to write the second half, the right-hand side of the energy equation, P1 over gamma plus Z1 plus V1 squared over 2G, B sub 2, sorry, I need to put 2's there, not 1's. And down here, P sub 2 over gamma plus Z sub 2 plus V sub 2 squared over 2G, okay? Now, for both of these, what's the pressure? 0, right? So these are both going to go to 0. And if we assumed that this was through some center line, and this happened to be my datum as well, it may or may not be, but then that goes to 0, right? What about the velocity? What's the velocity of the first one?
0.
Thank you. This goes to 0. Does this one go to 0? No, it does not. Okay. So if you have a free discharge, you cannot assume that the velocity goes to 0. But in this case, you can. However, In this case, you have an exit loss because the velocity does go to 0. In this case, you do not have an exit loss because there is no change in the velocity. We'll only have a minor loss if there is a change in direction or if the fluid has to accelerate, decelerate. When I say direction, I mean going around a corner. Going through a valve could also be a change in direction, right? A change where it accelerates or decelerates. This here is a deceleration. It's almost, well, it's exactly like a large expansion. And we're going to talk about energy grade lines today, and we'll see that the energy loss through here, we have a velocity coming through here, some velocity v sub 2, and then when it goes over here, it goes to 0, so we lose 1 velocity head. That's why for an exit loss, K is equal to 1, because we lose 1 velocity head. Kind of makes sense, doesn't it? All right. Now on the other end, if we have a pipe going from a tank, so if we have our tank here and here's our pipe coming out here, and the flow is coming from all directions and has to go around this corner to get into that pipe, well, this right here is a sudden contraction. It's a big sudden contraction. Now the minor loss for that, if it's a square edge, if it's a, you know, if it's butted up against that pipe, if it's 90 degrees square, whatever you want to call that sharp edge, K is typically 0.5. Now, if we round that just a little bit, if we put a little round right there, we can actually make that essentially go to nothing where K is equal to 0.03. Okay, and you say, well, why aren't more of those rounded? Because it's very expensive to round them. And so a lot of times they just weld them up square and they say we can deal with that little bit of loss because even over time, it's not that big. All right, but two standard losses, or loss coefficients, K is equal to 0.5 for entrance, unless it's rounded in some way, and then it could be anywhere, once again, from 0.03 to somewhere up to 0.5. It can vary depending on how much you round it. And exit losses, it's 1. Now, potentially, you could have like a culvert going out into a ditch, and the ditch still has velocity, but a lot of times we'll still treat that as a full exit loss, to be a little bit on the conservative side, because we don't know exactly how much that velocity is changing. All right. Okay, we comfortable with that? What?
Does rounded edges affect the exit loss at all, or does it not make a difference?
Oh, that's a really good question. Excellent question. And if you go to most hydropower plants, a turbine, all right. Well, I'm getting a little ahead of myself, but you asked the question, so let's go ahead and talk about it. Well, maybe in the second part I'll wait here, but let's look at this. If I have a pipeline coming in and I put in a turbine, and the turbine comes over here and goes into this tank, now based on what we just learned, you know that we have an exit loss right here, right? Of K is equal to 1. And so the total loss at the exit, so H exit is 1 times V squared over 2G. And if we're trying to maximize the energy coming out of there, you say, well, wouldn't it be better if we rounded those a little bit? Well, the rounding's not going to do you much because it doesn't have time. How to put this? Okay, let me say it like this. The exit loss is a function of the change in velocity. And the rounding on the upstream side allows the flow to enter the pipe smoother. So let me jump back up here. So if this is square edge right there, what are colors? What happens is the flow has to get up and around, and it can't move around that very easily. And so it creates a separation zone right here. And the actual opening where, so if I have a pipe this big, the actual opening where the flow is really flowing is this big. So we're shrinking it down. We call that a vena contracta. So we're actually reducing the area. You reduce the area, what happens to the velocity? the velocity goes up, right? If the velocity goes up, the velocity head goes down. I'm sorry, the velocity head goes up as well. So the head loss increases because of that large vena contracta. Well, on the downstream side, if we just make it smooth really fast at a nice rounded corner, that really doesn't change the velocity because there's no time for it. But if we put in an expansion, so if we come in here and we say, okay, here's our turbine, and now we're going to come out here and we're going to put in an expansion in to our tank. Guess what? K is still equal to 1, but V is small. Therefore, the velocity head is small. Therefore, the loss at the exit is small. So really, it's kind of the same concept. The vena contracta is naturally formed due to that sharp edge. But really what causes the large increase and why we need the exit or the entrance loss is because it changes the area that the fluid actually, how long it takes to turn that corner. And we use the same principle on the downstream side by using an expansion. What they call this is we recover the velocity head. It allows the fluid time to convert it back into pressure head. And by converting it into pressure head, that just allows us then the ability to use that in the turbine rather than burning it up as it goes out into the tank or the river or wherever the water goes. Okay, so it's an excellent question, good concept to help you understand entrance losses and minor losses. All right. Any other questions on that? Let's see how many we got on. Only 6 today. Well, all right, let's do this. Concept question for you. I have 2 reservoirs. Okay. I have 3 pipes connecting those reservoirs. So pipes A, B, and C. All pipe values are the same. The lengths are the same. The pipe type is the same. The pipe diameter is the same. The entrance and exit losses are the same. Everything's the same. Now, when I brought this problem up several years ago, I had a student say, well, that's not physically possible. Is it physically possible? You say, could I have a pipeline going across the bottom here that's exactly the same length as the one coming up from the top down? Some of you shaking your head no. Some of you shaking your head yes. If you're shaking your head no, you're thinking in 2D. You got to start thinking in 3D. As soon as you start thinking in 3D, you're like, oh yeah, it is possible, right? I can have that because the pipes aren't necessarily right next to each other. Or I can have the one on the bottom that snakes just a little bit, but still it accounts for, you know, everything's accounted for so they match up perfectly. But that's not the concept I want to test you on here. I'm asking you which one has the highest flow rate. That's what I want to test you on right now. Which one of those has the highest flow rate?
I would guess B.
Okay, so we've got a vote for B. And why would you say B? What's your logic for B?
Well, the closer to the surface that B discharges, the less water it has to push out of the way, which would result in less of a K value at the exit of B, where A and C both have a really high exit loss potential down there at the bottom because they've got basically more water to have to push out of the way and there's more of a velocity hit. But if B was discharging it near the surface of the second reservoir, there would be less water to have to push out of the way.
Okay. Well, that's a
I
beautiful
don't know if
statement.
that's real, but
And Scott, I really like that. It's a beautiful statement because that brings up another question when it comes to water flow. And let's talk about that while we're still thinking about this one. I don't think I've brought up the concept of water friction in this course yet, have I? Okay, so my hand here, I'm going to put it on this desk, and by pushing down, I can create friction, right? Comfortable with that? And that friction, if I push harder, I might break that so I better not push too hard. If I push harder, the friction force is greater, right? Okay, that makes sense. Why is it greater? What's the friction force a function of? The normal force. Great, it's a function of the normal force. Okay, well, let's jump back for just a second then. Then we'll come back to this problem. But let's say that we have two pipelines. And this pipeline here, we have flow going down, and we have P is equal to 1,000. And down here, P is equal to 990. And we have a second pipeline down here, P is equal to 20. And down here, P is equal to what? They're the same pipeline, same diameter, same flow rate. Now think about this. P is equal to 1,000 PSI. Isn't that equivalent to a normal force? It's pushing on the walls of that pipe even more, trying to break the walls of that pipe. So do you think on the second one down there, the flow is going to be, the head loss is going to be less than the difference up here? Because up here I have a delta P equal to 10 PSI, right? Oops. 10 PSI, we'll put units here. This could be kilopascals. If you are more comfortable with kilopascals, it doesn't matter. But my delta is 10 PSI. The pipe's the same length, same size, the same diameter, the same type of material. What's going to be the pressure on the downstream side of that? Same flow rate, everything's the same. This is the beautiful thing about fluids. What? I'm pushing harder on the pipe, don't I get more friction loss? You show me in the equation of friction loss where pressure comes into play. Doesn't. So the pressure on the downstream side of that pipe is going to be 10 PSI. Delta P is 10 PSI. So it doesn't matter how much pressure I put on the pipe. What it relates here is the difference. Okay. So coming back to this concept here, Scott brought up a really interesting point, which I believe is very intuitive, but is it correct? What drives the flow?
Head pressure.
The head differential between these two. Is the head differential any different for any one of those three pipes? Thus, they should all be the same. The flow rate in all three of those pipes is the same. Make sense? No, but it is the truth, right? In fact, Scott, it's like I paid you that to come up with that comment or with your explanation, because it's a beautiful explanation of what actually makes sense, doesn't it? I mean, yeah, you're pushing against less flow, you're going to get a higher flow rate. There was a senior design team probably 3-4 years ago, that nuclear engineering team, and they had to get water in a basin, okay? And so they had a tank up here. There's a bigger tank. I'm not drawing this to scale, obviously, but, and the distance and number of elbows and everything was about the same, but they thought, well, let's run a pipe down over here and we'll put it just above the water surface, okay? And it was a couple inches maybe, all right, we'll say 2 inches. And the other pipeline came over here and went in through the bottom. And once again, the lengths were essentially the same, just due to the configuration. And they were claiming that the one that was free discharging was going to have a higher flow rate. Would you agree with that? Based on what we just talked about? No, you shouldn't, because the head differential between this right here versus the head differential of this, we'll put H1 there and H2 here. H2 is greater than H1. H2 has more gravity to push the flow, even though it has all this water on top of it. Doesn't matter. We're talking about the difference between the flows. So this one actually comes out, and there's less gravity pushing it.
So that one's actually lower.
Yeah, this one here, if everything else is equal.
So then what happens once it fills that one more and it rises and that one becomes less?
So what we're talking about now is a steady state, everything's constant,
Oh,
okay? Now, if we're talking about what happens in time as that comes up, if the water level came up to here, then they would be the same. Then the flow rates would be exactly the same, because now they're pushing against the same head differential. Okay. Some of you, and it's hard to tell with just the eyes, but some of you are still like, what? How are we doing? Make sense? Okay. So with that in mind, now what we want to work on today is EGLs and HGLs. So EGL is the energy grade line, and HGL is the hydraulic grade line. Okay. The equation for each one of these, the EGL is P over gamma plus Z plus V squared over 2G. And the hydraulic grade line is P over gamma plus Z. So it's possible for the HGL to equal the EGL, but it's also possible for it to be less if there's velocity. Okay, so the EGL is always at the HGL or higher, has to be. Because V squared, even if you have what's called a negative velocity, which is just velocity in the opposite direction, still let's get squared, and so it's always going to be a positive value, right? Now EGLs and HGLs are a graphical representation of how the system functions. Okay. Graphical representation on how the system functions. Now, a lot of students tend to think that this is an academic exercise. We only do this because we're in school. They don't use this out in practice, but that is not true. Now, you're not going You're not going to do design with numbers off EGLs and HGLs, but they provide a method of looking at a system and at a glance knowing exactly what's going on and identifying key areas that you need to be concerned about. And practicing engineers that know what they're doing use it. I had an opportunity a few years ago. There's a company out of Texas, Freeze and Nichols, that does, I mean, they're kind of regional, but they're huge down in Texas and the southeast area. And they do a lot of dams, and they contacted me and they had a question about one of their projects. And I was kind of swamped, and I have a good colleague down at Utah State that also does a lot of work with them. And I gave him a few ideas, and I said, look, I don't have time to dig into this like you need. Call Mike. And, you know, Mike does a great job. And they're like, yeah, we're going to contact him as well. And I said, well, you know, based on the ideas that I've given you, you know, let me know what Mike tells you, because I know he'll have time for the in-depth, and I'm kind of curious to see how he approached this problem. And guess what? He did exactly the same thing, but what I was thinking is he sat down and drew up the HGLs and the EGLs and said, okay, here you go. Here's kind of the areas, and then he put the equations to match it up. So EGLs and HGLs are graphical, and they help you understand concepts. And we're going to use them in the coming weeks as we talk about pipe networks. So I want to explain to you how we draw EGLs and HGLs. You already know what they equal here as far as their value goes. And once again, they're representative, so we're not worried about getting the exact value. We're not going to pull out a ruler and scale these. We're going to draw representations to give us an idea of how they work. So I have posted on Moodle a handout. And here we go. Okay. All right. So I want to kind of run through this so you get an idea of how EGLs and HGLs work. Note that the line of an HGL represents the friction loss in a pipe. Okay. If a line is steeper, it means we have greater friction loss. So let's see how this works here, see if we can get this to work. Okay, so you'll notice right here, we have a contraction. Okay, contraction changes the flow from low velocity to high velocity. Well, higher velocity pipes have a greater loss. Hence, our slope of our line over here is bigger. Okay, so simply looking at that, if I didn't know what kind of pipeline I had down there, I could look at that EGL and HGL and know exactly what's going on. Boom, there's a head loss. I mean, there's a contraction right there because we change velocities. Velocity head changes, so the velocity changes. All right. We started up here. The EGL and HGL are together because there is no velocity in this reservoir. And then as the velocity goes through this rounded corner, the HGL forms and tracks it. They are parallel. The difference between them is the velocity head right there. That's the difference in between the HGL and the EGL. When we come down here at the outlet, we have the velocity that's going into the pipe right here. And hence we lose one velocity head at the outlet. Hence the minor loss for an exit is 1. Okay. So slope represents the head loss, the friction loss in the pipe. And jumps in the pipe represent minor losses. Okay. Any questions on that? So if I was doing this problem, if I had these two reservoirs, I would say, okay, I'd come up here and say I have an HGL right here and an EGL over here, one down there. And I would identify then that I would identify, okay, close that out. I would identify, it's not a very straight line, but something's going on right there, you know. I guess actually right in that range right there, okay? So looking at that line, and sometimes this is trial and error, but you know, you kind of say, okay, if I come in here and then right there I do this sharp curve down because I have a change in velocity, then I continue down, one exit loss down there, and then my HGL is going to come down and also then curve down and go down. So it's just kind of trial and error. Once again, they just need to be representative. They don't have to be completely accurate, okay? All right. Whoops. Huh. That's really weird. There we go. Okay, let's go to the next one. This is one of the key things with the HGL that is very useful in practice, identifying low pressure regions, especially negative pressures, because negative pressures are a real problem in pipelines. And we talked about this, right? You went down to McDonald's, bought yourself a drink, grabbed the straw, and you put the straw in your mouth, put your finger over the end, and tried to blow that straw up. You couldn't do it. You couldn't get that straw to explode. But if you apply a little bit of vacuum, does that straw collapse? Oh yeah, like that. Pipelines are the same way. They're extremely well at handling pressure going out. Anytime you get a negative pressure, they just collapse, especially if they have a soil load on the outside that's trying to push them in as well. So they're just going to fold right up, okay? So finding low pressures, negative pressure specifically, are what we want to do. And the way we find this is, look right here, this is a simple tank, and here's one of the rules: an HGL will always go through the middle of a free jet because there's no velocity. So it always, and there's no pressure either on a free jet. So all we have to do is take into account is the elevation head. Let me say that again. For a free jet, the HGL is in the middle because it's the elevation head. No pressure, there is velocity. I said that wrong, didn't I? There is velocity, but there is no pressure. So we go to the middle for the HGL, and of course the EGL is above it. So that represents then the velocity head, right? So rule, free jet, HGL is in the middle of it, okay? So if that's the case, and I come up here to my reservoir and say, okay, well, I'm going to go from 0, and then I like to start back here just a little bit, but come back here and then identify that my HGL is going to go down here. It's going to be a straight line because that's a constant diameter pipeline right down to the middle. That's my HGL. And if I know that's my HGL, but my elevation up to this point up here, here's my datum down here, and I got to go all the way up to the center line. And I know my HGL is now underneath that. What does that tell me about that pressure head? Which way is this arrow pointing? Down. Because I go up to the center line of the pipe, have to come down. In order to get back down, I have to have a negative pressure head, which means I have a vacuum in that pipe or a negative pressure. Because remember, HGL is equal to P over gamma plus Z, pressure head plus elevation head. So if I have to go all the way past my HGL to get up to the center line of the pipe, that means I have to have a negative pressure head to come down. That's important. Okay. All right.
How much difference in pressure, as far as having the pipe collapse, could there be? Like if that pipe could hold 500 PSI, how much of a vacuum would it take for it to collapse?
You know, that's hard to say because it's all a function of what is the depth, what is the soil load pushing in on it, what is the type of material. Some materials do well under compression, which would be like if it was concrete pipe. Concrete pipe takes compression very well, right? But it doesn't take tension very well. So concrete pipe, may last a little longer than say PVC. And so even though PVC could hold a 500 PSI if it was properly designed really well, a couple of negative pressures on PVC will make it fold. Whereas concrete pipe would have a tougher time holding the 500 PSI in pressure, but it would do a better job of holding the vacuum. So yeah, it's just dependent upon the material. So you just have to kind of look at what the material is and what is the soil load around it. Because soil loads can actually help hold high pressures, can actually help build a casing around the soil, if you will. But in the reverse, they can also help collapse it. And there's some design manuals out there on that. You go to the type of pipe. Concrete pipe has their design manual. The Plastic Pipe Institute has theirs. And so you just look at what there is. Okay. All right. So here's a turbine. All right. And so what I want to highlight here is that a turbine removes energy from the system, right? So as we're moving along right here, we have a relatively shallow or flat friction slope, and then we get to the turbine down here, and we have a huge drop in both the EGL and HGL because they're taking energy out of our system. And then because we do an expansion down here, you can see what happens to the HGL. The velocity by the time it gets to the tank is almost nothing. Because remember that velocity is a function of the area, and area is a function of the diameter squared. So a small change in the area, small change in the diameter makes a huge difference in the area, which makes a huge difference in the velocity. And so you can see that that goes to zero pretty fast or negligible, right? Concept question here, would it matter where I put that turbine? Could I put that turbine up here and extract the same amount of energy out of it? So let's assume that this was my turbine. There's my turbine right there. Could I extract the same amount of energy out? Well, yes, I could, but what's the problem here? If I was to draw the HGL, I would come down here, and then I would, so if I take that same distance there, that's about right there, and then this would come across, yeah, it would come across here, and then of course I would have that expansion, it would go right there. Redraw that. Okay. So the answer is yes, I could pull the same amount of energy. Same amount of energy is available, and I can stick it up closer to there. What's going on right in here, though?
Negative pressure.
Negative pressure. So as long as my design correct, as I design my pipe to handle the negative pressure, I could put my turbine up there. It'd still work. Because the driving head in this system is the difference between those two reservoirs. Okay. Any questions or comments on that? Okay. All right, constriction. Pretty basic on this. My EGL and my HGL near each other. They're parallel. And the slope of the line represents then the friction loss coming down, right? But then as I get down here and I have a constriction, my HGL changes. Why is my HGL curved rather than being just straight? E is equal to Q times A. A is equal to B squared over 4. B squared. As my diameter changes, my area changes as a function of diameter squared. squared means curved, right? It's not linear. So a linear line there would not be appropriate, although it really doesn't matter that much. It doesn't make a huge difference. But if you want to get really technical, it would be that curved line because our velocity is changing, which means we tend to get more and more velocity head the closer we get to that nozzle. More velocity head means a bigger differential between those. All right. Once again, that's not that big of a deal, but just trying to help you understand the finer details. Okay. All right. So what would happen here if I stuck a piezometer or a static tube in my system? So this represents right here, this is a piezometer. All right. Piezometers, oops. Piezometers capture the hydraulic grade line. They do not capture the velocity. The stagnation tubes capture the velocity. So that's why this stagnation tube right here takes the flow up even higher and gives us then the velocity, which gives us the velocity head, differential between those two. So piezometer or a stagnation tube gives us HGL or EGL respectively. Okay. I apologize. I should have emailed the class and told you that, you know, we're going to use this in class if those that wanted to have a printout of it before class or during class. So I'll try and remember next time when I post something like this to tell you to print it out before class. Okay, pumps, just the opposite of a turbine. Okay. They add energy to our system. This is the only time an EGL can go up. HGLs can go up if we change the pipe size, right? If I go from a small pipe to a large pipe, the velocity now changes from a high velocity to a small velocity, so my HGL can actually go up because my velocity heads are different, even though I may have a minor loss there. But the EGL cannot go up. The EGL can only go up if we have a pump. Not possible. Unless you're adding energy to your system, it cannot go up. And the only way to add energy to a system is with a pump. Okay, so here we go. We add in head of the pump, both the HGL and the EGL go up, and then they continue on their merry way if the pipe size is the same size. So that's why the slope of these two lines, these four lines, are the same because the pipe size stays the same. Okay, that is the last diagram of the EGL and HGL. You feel like you have a pretty good handle on it? Any questions on those? That's what the homework's going to be. It's going to be drawing the EGL and the HGL. Okay. All right, in the last few minutes here, I want to kind of set us up for what's coming on Wednesday. And I would note, just a reminder that the test is on Friday. We will talk about the test on Wednesday. I'll have a study sheet for you. Okay. But then when we get done with that, unless you bring a lot of questions, we're going to start talking about branched pipes. So up to now, everything that we've done has been a single pipe. Even though that single pipe can change diameter, it's still been one single conduit going down the path. Now we want to talk about what happens.
You can switch your.
Oh, thank you. What happens when pipes may branch or converge? Okay. So for example, if I had pipe A come along right here, and then it split into B and C and came back together into pipe D, how do we handle that now when there's multiple pipes? Okay. And we are going to continue to use the energy equation to solve this. This is going to take us into what's called three reservoir problems, which is going to lead us into pipe networks, which could be anything from the city system to a lawn sprinkling system, to a industrial process where there's multiple pipes and we have different valves and we send flows around different ways, and that's going to take us into solving those types of problems. All right. Any final questions for today? Okay. Wonderful. So you guys have a great day, and we will see you on Wednesday.